Hello and welcome to our film about the project Reservoir Computing. Firstly, let me give you an overview of our contents. Our first topic will be the history of machine learning and a short explanation of some very common methods. After that, we will explain reservoir computing and the difference between normal neural networks and reservoirs. Then, we will continue with our specific use cases. First, we programmed the reservoir for function prediction. Secondly, we used the reservoir for signal differentiation. In the end, we will give you an outlook and what to expect from reservoir computing in the future. Now I will introduce you to the beginning of machine learning. First, when computers were invented, people used simple algorithms. Algorithms consist of well-defined instructions that the computer can work itself through. Algorithms have a given input and produce an unambiguous output. In the 60s, people started thinking about making a smart computer, which can learn by itself. The idea of machine learning was born. Engineers thought building it like the brain is built. The brain consists of neurons and synapses. The synapses are connecting different neurons with each other. If you learn something new, the connection between neurons strengthens. Over time, if you do not use certain knowledge or forget something, the connection can grow weaker. With this idea in mind, engineers created the perceptron. Dennis is going to explain it shortly after me. At first, there was a software-based implementation, but shortly after, the Mark I perceptron was built. You can see it here on the picture. This was the first hardware-based implementation of the perceptron algorithm. It was designed for image recognition. As input, it used a 20 by 20 photocell camera, making it a 400 pixel picture. The connection weights were encoded in potentiometers and adjusted by small electrical motors. As you can tell, the machine was rather big for computing only a 400 pixel image. The perceptron seemed like a very promising concept. The New York Times wrote, based on a statement from Frank Rosenblatt, the inventor of the perceptron algorithm, that the perceptron will be the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. As you all know, we do not have a computer which can do all of that. Back in the time, it was quickly proved that the perceptron could only recognize a few patterns. Due to that, the research in machine learning stagnated for a long time. It was only until the discovery of multi-layer feed-forward networks, which Dennis will also explain in a short time. Even though the basic algorithms existed, the hardware lacked computational power, and the algorithms were not perfectly optimized. However, we all know that since the 60s and 70s, computers and optimization have come a long way. Hence, the hype for machine learning and especially deep learning. Today, most machine learning concepts moved away from the simple biological concept of neurons and synapses. Liquid-state machines are an example for a reservoir computing algorithm which still uses the biological template.
Hello, I am going to give you a short overview about the single-layer perceptron. It is a linear classifier that looks out for a hyperplane to divide several test variables into two possible states, for example 0 and 1, or more application-oriented cat and dogs. The use of simple layer perceptrons are the calculations of simple Boolean functions such as OR, and not. With the following pictures and formula, I will try to explain how this algorithm works. The axes are the inputs. The W, which you can see in the picture here, gives them the right weights to calculate the output. This W needs to be trained. In addition, the bias is an extra into an input, which generally also need to be trained. It gives more flexibility, but is not necessary in the single layer perceptron. F is the activation function. It is necessary for compute the output. A great discipline is to find the right amount of training objects, because too less means underfitting and too much means overfitting. An example for underfitting you can see in the picture here. In the case of the single layer perceptron, it is common to use the Heaviside function and take the negative threshold for the bias. The training of a perceptron algorithm is supervised. This means we know all the labels of the test objects during learning process. The algorithm works as follows. If the output was correct, we don't have to change anything for the weight. If the output was 0, but it needs to be 1, we have to add And if it was 1, but it needed to be 0, we have to subtract alpha times x. Alpha is the learning rate. It is needed for secure near solutions for getting far away distracted again. This learning procedure can teach all solutions a perceptron can represent. This is proven by Rosenblatt. Limitations of single-layer perceptron. The limitation of single-layer perceptrons are complex classifications like the XOR problem. As you can see, separating datasets of the OR problem is not a big deal. But what can we do with the XOR problem? It is impossible to separate these two datasets with a single straight line. But what if you create two single-layer perceptron and use them as an input for another perceptron? In fact, this approach works because the XOR disjunctive normal forms, which you can see here. And just as I told before, the simple AND, OR and NOT can be calculated by a perceptron. Nested perceptrons are called multilayer perceptron. In this example, it is two-layered with a hidden layer. This picture shows graphically one of the solutions of the XOR problem by using the second disjunctive normal form. The result is 1 if only one of the input is activated but not both. Tau is the threshold that needs to be exceeded for the neuron to fire. In the learning procedure of the multilayer perceptron, we must do backpropagation with gradient descent. We will minimize a loss function, which is usually the squared Euclidean distance between the given and the calculated output, because we must use the chain rule to calculate the derivatives needed for the gradient. Very complex and unhandy terms will appear. As you can see, even with one hidden layer, the exact derivatives are very complex. But imagine you have 100 hidden layers. This would make the terms explode. The calculations are very unpleasant, so we need an alternative method. For the training of neural networks, only derivation values are of interest, not formulas. A good compromise is therefore automatic differentiation. Every complicated function can be written as a sequence of simple functions. This is a computational graph. It shows how the separation works. The automatic differentiation uses the chain rule, which you can see here. So not only the values of each node before is necessary, but also the derivatives.
Now I'm going to explain recurrent neural networks. As the name suggests, we not only have connections from one layer to another, but also we got connections between two neurons in the same layer, described via WL in the picture. A neuron can also be connected to itself, WD. Moreover, in recurrent neural networks, we even got connections going back in the layers, WI. Due to that, information can stay for a longer duration inside of the network. The neural network has a simple version of memory. If we now use sequential input data and compute their output at any given discrete time, the recurrent neural network can learn to handle text and speech. The training of recurrent neural networks can be done with gradient descent that Dennis described earlier as well, but we are computing time-dependent data. Therefore, we cannot use the same exact backpropagation the multilayer perceptron needed. We need backpropagation through time. For this, we are unfolding the network. Hence, we get k neural networks with the same parameters, but different inputs and outputs. Here you can see a recurrent neural network with a recurrent layer f and a feed-forward layer g. We are then unfolding the recurrent layer for the first 3 time steps. Hence, we can see exactly how the output at t plus 3 is computed. After unfolding the neural network, we can use backpropagation to find the gradient of the cost. It is crucial to understand that each instance of f in the unfold network shares the same parameters like weights and biases. As you can tell, the unfolded network can get very deep, depending on the length of the input sequence, and therefore we need automated differentiation for saving computational power. With very deep neural networks, vanishing or exploding gradients can occur. For example, in the sentence I grew up in Germany, I can speak German fluently, the connection between German and Germany is very important. The network needs to understand this. This is called a long-term dependency. In terms of sequential data analysis, the distance between the dependent words is long. During the training of the neural network, the gradients are being propagated back in time all the way to the initial layer. The gradients from the lower levels need to go through continuous matrix multiplications because of the chain rule. We all know that if you take a number which is just a little bit above 1 and take it to the power of 100, meaning you multiplying by itself, it can grow very big. We can have the same problem with backpropagation. If the spectral radius of the matrices are above 1, we got an exploding gradient. However, we neither can scale the spectral radius between 1 and 0, because then we would get a vanishing gradient. Therefore, the information would disappear in our network. This is a huge problem in deep machine learning, but several approaches to solve this exist, like gradient clipping and long short-term memory. Now I'm going to give you an overview of the idea of long short-term memory. Sepp Hochreiter and Jürgen Schmidhuber proposed the idea of LSTM in 1997 to deal with the vanishing gradient problem. In an LSTM, the simple neuron is replaced with a more complicated unit, which gives the ability to let the backpropagating gradient through without changing it. Here you can see how a peephole LSTM unit is built. It consists of a cell and 3 gates, which control the flow of information inside the unit. The cell is the memory part of the unit. The input gate controls how the input from another unit is handled. The forget gate can keep information inside the unit, and the output gate controls how the value of the cell is used to compute the output of the unit. Each of the gates is a single neuron. The connections between the gates and cell need to be trained during the learning phase. They determine how the gates operate. As you can see, some of the connections are recurrent. The 3 connections from the memory cell C to the gates I, F and O are called peephole connections. These connections determine the contribution of the state of the cell at the previous time t-1. The big circles containing an S-like symbol represent the application of an activation function, like the sigmoid function. The small circles with x inside represent an element-wise multiplication of its inputs. Now you got a basic understanding of a long short-term memory unit. The LSTM can be trained using gradient descent and backpropagation through time. Due to the construction of one unit, the backpropagated error remains inside any unit, and hence the vanishing gradient problem is solved. Exploding gradients can still occur. This is only one way to build a long short-term memory. Several others have been proposed, and they have less or other gates. Since 2016, big technology companies like Google, Apple and Amazon use LSTM in several products. For example, Apple and Amazon use them for their speech recognition software, Siri and Alexa.
Recurrent neural networks are good machine learners but have one major sobering disadvantage. The learning process has long and complicated calculations because of the non-linearity and backpropagation through time. This leads to the fact that much computational power and a long execution time is needed. It would be nice to have an alternative method that is as good as a recurrent neural network, but is more computationally efficient and has a time-saving learning phase. To achieve this, a random recurrent network is initialized at the beginning, which inner weights are not trained during the learning phase. The only part that is trained now is the readout mechanism, which you can see on the picture. To train the weights, only solving a linear system of equation is needed now. This can be done by linear regression. This is the current state of the art in computational power. The reservoir here is the big square which you can see in the picture. Likewise, you can see that the readout mechanism doesn't only read the reservoir, but it can also use to read the input units. But this is not always necessary. Likewise, the feedback can be helpful for some problems too. It gives information for the output layer back to the reservoir again, but it is specific when it is useful and when not. The readout and the input layer are fully connected. The rest has a sparse connectivity to avoid over and underfitting. The fact that the weights inside are not trained anymore is the reason why we call it reservoir. In context of recurrent neural network, we talk about echo-state network. But there is also a different approach named liquid state machine derived by spiking neural networks. The difference is that the spiking network is more biological motivated, recurrent neural networks are not. The activation function of a liquid state machine is the heaviside function. It gives a binary output, while the activation function of an echo-state network is continuously like the sigmoid or the hyperbolic tangent function. The output here is not binary, it's more like a percentage probability. Like in the recurrent neural network, the reservoir computers can handle sequential tasks like speak and text recognition. To give you an insight into our project, we have decided to show you some applications examples. Because we had no adaptive solution, the biggest problem was to manually select the right connectivity and number of neurons. With the following pictures, I intend to show you exactly what I mean. Note that I'm not showing you the specific number of neurons or the percentage of connectivity that I have indicated every single time. The reason for this is because every problem is different and telling you the specific values doesn't help for understanding. You have to check which values give the best prognosis individually for every problem. Notice that some tasks need more neurons, but make sure to also reduce the connectivity to keep good results. There are 4 colors at each picture. The blue ones are the original outputs of the training set. The orange ones are the trained outputs of the training set. The red line are the outputs from the test set and the green one for the guessed ones. To give you a small overview, I will now introduce you the sinus. Well, that is a sinus. I know this is very deep mathematical stuff, but we must hang in there to understand the problem. If you have been listening, you will have noticed that we have created a training and a test set for all our problems. The training set should teach the program how a sinus works in this case. As you can see here, the near future is predicted very well, but at second 12.5 seconds, the prediction will get worse due to the small interval of training data. So we tried to fix that with a bigger interval. Look, if we train it with a longer interval, we can see that the future can be predicted almost perfectly for a long time. In the beginning, we tried to run our problem with 1000 neurons to be sure that we had enough. However, as I told before, it was hard to find out what value for connectivity is good to get a useful result. In this picture, I have shown the problem of 100% connectivity, alias all-to-all connection, in the reservoir. The values are exploding. Reaching values around 10 to the power of 7 is reproducible then. Another problem arises when the connectivity is too low. The problem here is that this will make the reservoir useless because every information keeps inside the reservoir with no chance to get out due to missing connections. Here is another picture by rerunning the same program. As you can see, the prediction is different every time, what makes the result very useless. 3% connectivity seems a good value for 1000 neurons. We asked ourselves if the program could handle the same tasks as good as before with a lower number of neurons. So we tried to do it with 100 neurons and noticed that 30% connectivity gives the same reproducible results. So can we get any good prediction if we use 10 neurons? The answer is no if we keep the same amount of training data. But the answer is yes if we reduce it. Look, like I said, the green line is the prediction from the program and it looks very accurate with a 30% connectivity. Our next aim was to teach the program how the exponential function works. So as always, we put in some training data and test data. We found out that the near future is predicted very well, but as far we get away from that training set, the worse the prediction gets. Just like it was with the sinus, a bigger test set can help, can't it? The sad answer is no. We tested it and recognized the same pattern for every training set we typed in. The echo-state networks learn simple correlations, but as we all know, the exponential function does not have an easy correlation. The sinus is also complicated but has a repeating pattern. Our echo-state network can also handle multiple inputs and outputs. Here is an easy example. I gave the sine and the cosine as an input and tried to compute the addition and the multiplication of them. This was no problem. Notice that I just showed the guessed and trained datasets, not the original here, to keep the overview. Due this works very well, I tried complicated output like the nested function of my input value, like cosinus of sine, and the derivative of that function. As you can see, the echo-state networks can handle it very good too. So we can try harder examples like the classification of an input data, which Leon will explain you now.
In our second use case, we wanted to train our reservoir to differentiate between a sine and a delta pulse. This is a kind of binary classification. If a sine is detected, the output of the reservoir should be 0. If a delta pulse is detected, the output should be 1. 1 and 0 are the class tags. Our training data was a randomly generated sequence of sine and delta pulses with fixed lengths. Here you can see a generated input with 10 pulses of the length pi. The blue line represents the randomly generated input, and the orange line represents the output we want from our reservoir. As you can see, the result should always be 1 when a delta pulse is given, even when the pulse is 0. This will lead to a small problem, as I will explain in a second. For this task, we did not use feedback. Here you can see how well our reservoir did in the training. The reservoir got the blue line as an input and computed an output for our readout. The readout then tried to match the result from our reservoir to the orange graph. This training resulted in the green graph. As you can see, we always have small fluctuations of the result from our readout. This is due to the nature of our activation function and the periodic behavior of our input. We could interpret the results as an estimation of the two class tags for sine and delta pulse. If we do this by just rounding the numbers to integers, the orange and green line are matched perfectly, as it is plotted in this graph. The classification worked flawlessly. Now you can see the performance of our just trained reservoir on unknown test data. The result meets our requirements. For a better overview, we did not round the data to get the class tags. The biggest error, aside from the very first point, occurs when two sine pulses follow one another. For a small period, the input function is 0, and the reservoir probably interprets this as the beginning of a delta pulse, hence the jump in the resulting graph. Our reservoir is a black box. We cannot know what features exactly were learned. But if we increase the length of the sequence, for example to 100, we can clearly see that the graph always jumps to exactly 0.5, because our reservoir just could not decide if it is a sine wave or a delta pulse. When training the readout over a longer input sequence, the results get more consistent. But it is also worth noting that our fluctuations increased. After training and testing our reservoir, we wanted to compare it to another network. We compared the sine and delta pulse classification with a two-layer feed-forward neural network. We used TensorFlow to build the network. As expected, the FFNN can't handle sequential data very well due to the lack of memory or feedback. It just learns to classify a data point depending on its value. Every point with a value of exactly 1 or 0 gets classified as a delta pulse, whereas every point with a different value than 1 or 0 gets classified as a sine pulse. A recurrent neural network along short-term memory could have helped. Now I'm going to give you a small overview of some promising looking concepts for reservoir computing, because reservoir computing will probably get more and more important in machine learning. At first, deep reservoir computing. For our use cases, we only needed a single reservoir, but like the multilayer perceptron and deep recurrent neural networks, it is possible to layer reservoirs after each other. Here you can see 3 different approaches for connecting reservoirs with each other. Connecting multiple reservoirs could potentially increase the memory capacity and the ability to work with different timescales, as stated in the paper Deep Reservoir Computing, a critical experimental analysis published in December 2017. Another way to improve reservoirs is to build them physically. At the beginning, we saw the Mark I perceptron, which was a hardware-based solution. Today, we can manufacture way smaller and better components. Especially the advanced production quality of fiber components could help building reservoirs. Here is a schematic of an optoelectronic reservoir. The red parts represent optical parts, whereas the green ones are electronic components. The way this works is just like the software-based reservoir. The input at the bottom comes from the AWG, arbitrary waveform generator. The combiner combines the feedback from the old signal with the new input signal. The optical attenuator is used to control the intensity of the feedback. The non-linearity needed for a reservoir comes naturally from the physical properties of the fiber optic cables. The readout gets optimized by a computer in a post-processing stage. Here you can see the result of the optoelectronic reservoir trying to differentiate between sine and delta pulse, like we did with our software reservoir. As you can tell, the result looks good. The normalized mean square error over 1000 inputs is 1.5 times 10 to the power of -3. In other applications, the results were comparable to state-of-the-art software-based solutions. Another hardware-based solution is quantum reservoir computing. In this reservoir, fermionic lattices are randomly coupled, J, Ij. This leads to the black box a reservoir represents. As well as for the optoelectronic reservoir, the connections are naturally nonlinear. The reservoir gets excited by an optical field. As output, the occupation number of the fermiotic sites are used. This reservoir can identify if a quantum state is separable and simultaneously estimate its various properties. That's it for this film. Thanks everyone for your attention. If you have any questions, don't hesitate to ask.